Hello everyone, welcome to Canal Physics. Today we will be learning about distance, displacement, speed and velocity. Before we start today's video, don't forget to buy your copy of Physics Foundations. Please click the link in the description below. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Now let's start today's topic. Let's start with distance and displacement. Distance, denoted with a lowercase d, is the length of the path taken by an object between 2 points, whereas displacement, usually denoted with lowercase s, is the length of the straight line from the initial to final position. And it's important to note that distance is a scalar quantity and displacement is a vector quantity. So distance doesn't require a direction, but displacement does. Let's start with this very simple motion of this bike rider. This bike rider has started here on the left, the initial position, and they have moved rightwards to this final position. And the amount this bike rider has moved is 7 meters. So I'm going to quote the distance and displacement for this simple journey. The distance d is simply 7 meters because that is the length of the path taken by this bike rider, whereas the displacement s is 7 meters right. The bike rider started in this position on the left, the initial position, and they were displaced to the final position, which is 7 meters to the right. So for this very simple one-dimensional motion, the magnitudes for distance and displacement are the same, but you just need a direction for the displacement because it's a vector. But with journeys that are not so straightforward like this one, pun intended, we must be open to the idea that magnitudes for distance and displacement, even for the same journey, can be different. Let's do an example for a more complicated journey. Here a person runs in a semicircular path. The radius of the circle is 25.0 meters, and we're asked to calculate the distance and displacement for this journey. Let's analyze this diagram. There is a little compass here. I'm sure that's going to be useful for the direction for displacement. And here is the semicircular path. We can see that the runner started over here, and they ran over here, and this is their final position. To answer part A, to find the distance for this journey, we need to recognize that this is half of a circle. And since distance is the length of the path taken, then the distance will equal half of the circumference of this circle. So recalling that the circumference of a full circle is 2 pi r, and the distance is going to be half of this circumference. So substituting the formula for circumference, we get 2 pi r over 2. And we can see that the 2's cancel out, so therefore the distance is simply pi times r. And substituting the radius and solving gives us 78.5 meters. Now for this journey, the magnitude for the displacement is not going to be 78.5 because this runner didn't run in a straight line. They ran in a semicircular path. So we must go by the definition for displacement, which is the straight line arrow from start to finish. So I'll draw this in with a vector so it's more clear. So this is the displacement vector for this journey. It is an eastwards vector, so I already know the direction. But the magnitude is easily solved simply by determining the diameter of this circle, which is simply double 25. So the displacement is equal to 50.0 meters east. And that's it. Let's learn more about displacement. Another way to define displacement is to say that it is equal to the change in position of an object, and we denote the position of an object with the lowercase letter x usually. Therefore, the displacement of an object s is equal to the final position x subscript f minus the initial position x subscript I. So therefore, we can also write it as delta x. In this example, we've got a motorbike moving at a constant speed v, or a uniform speed v, to the right, and their initial position is xi over here, and their final position is xf over here. So to determine the displacement, or the amount that this motorbike has moved in this particular period of time, we need to define an origin or some zero position point. Now this is arbitrary, this is not an absolute position, but we need a 0 point in order to determine the other values of position. So you can see by simply inspecting this diagram that the displacement between the initial and final positions must be xf minus xi. So you can imagine this line, this horizontal line, or the road, as the x-axis. And let's just assign some values to xi and xf so we can see this equation here for displacement in context. I'm going to say that xi is 10 meters and xf is 80 meters. So therefore the displacement is going to be xf minus xi, or 80 minus 10. Therefore it's going to be 70 meters. But we must not forget that displacement is a vector, so it requires a direction, and that's simply from this initial position on the left to the final position here on the right. So it's going to be a rightwards arrow. Now we can quote the direction for the displacement, which is rightwards. Two noteworthy things here is that we are becoming more familiar with notation that you might see in a formula booklet or a textbook, or even a question, and also that you need two different points to determine the distance or displacement of a journey, not just one. And that might be an obvious statement, but it's important to know that the object may not start at the arbitrarily defined origin. Like in this example, it did not start at the origin, it started at the 10-meter mark and finished at the 80-meter mark. So these 2 points were needed to determine the displacement or the distance, and we needed to subtract these quantities to determine that. Now we're ready to learn about average speed and average velocity. Average speed, which is a scalar quantity, is equal to the rate of change of distance. Therefore, the average speed is equal to distance divided by time. Whereas the average velocity, which is a vector quantity, is equal to the rate of change of displacement. Therefore, the average velocity equals displacement divided by time. And soon we'll discuss why the word average needs to be included, but for now we'll just calculate the average speed and velocity for the journey we looked at earlier. Let's assume that this semicircular journey took 14 seconds to complete. And I'll just write the distance and displacement we solved from earlier. Now you may have noticed we used the same symbol for average speed and average velocity. But don't worry, all that really matters is that you understand that average speed is the rate of change of distance, whereas average velocity is the rate of change of displacement, and you won't get the two mixed up. So using our answers from before, let's solve for the average speed and velocity for this runner. So the average speed is 5.61 meters per second. And how do I know meters per second are the units for this quantity? Well, a bit of dimensional analysis will tell us that 78.5 is in meters, 14.0 is in seconds, so meters divided by seconds is going to give me meters per second. And if you're not sure about dimensional analysis, please watch that video. Now solving for the average velocity. 3.57 meters per second. We must not forget that average velocity, or any velocity, is a vector quantity, so it requires a direction, and this is always just going to be in the same direction as the displacement, which it was calculated from, so also eastwards. And that's it. Just a side note before we move on, whenever we say rate of something, it simply means that something is divided by time. Let's revisit the situation from before with the motorbike to understand more about average velocity. Before we just looked at the initial and final position and subtracted them to get the displacement, but if we introduce the variable of time, this will allow us to calculate the average velocity of this motorbike between these 2 points. What you need to imagine now is that there is another person recording the time when this motorbike passed position xi, and yet another timer over here, recording the time when the motorbike passed position xf. And for these measurements to make any sense, to give us the average velocity eventually, they needed to both have started their timers when the motorbike was at the origin, which is also the point where we're going to define the time was 0, because that's when both timers started their stopwatches. So just like I did before, I'm going to assume that this xi position is 10 meters, and the xf position is 80 meters once again. Now I'm also going to make up some values for ti, the time recorded by the first timer, and tf, the time recorded by the second timer. Let's say time ti is 0.4 seconds and tf is 3.2 seconds. Now we can calculate the average velocity of this motorbike between these two positions. So let's substitute all these values in. So we have 80 minus 10, the difference in positions, divided by 3.20, take away 0.40, the difference in time measurements, which gives us 25 meters per second. And don't forget, velocity is a vector, so we need to write the direction as well. And as always, it's going to be the same direction as the displacement. And that's it. Let's do a two-dimensional example. A person walks 4 meters west and then 3 meters south, the journey took 10 seconds. We're asked to calculate the distance, displacement, average speed, and average velocity. And again, we're going to soon explain why these are average values, but that's not important for right now. I'll start by drawing this journey. So I've done enough groundwork to determine the distance, which is going to just be 4 plus 3, because that's the length of the path taken. So that's nice and easy, just 7 meters. To determine the displacement, part B, I'm going to need to draw in the displacement vector, which is going to be from the initial to final position. As so, here you can see that S represents displacement, and it is the hypotenuse of this right angle triangle. Therefore, I use Pythagoras' theorem, and that turns out to be a nice integer, 5 meters. So to have the complete answer, we need to get the direction, and we do that using the triangle. So theta is going to be the direction that the displacement is heading in. So theta is here, and I'm going to solve for theta using trigonometry. And theta is 36.9 degrees, rounded to 1 decimal place. Keeping in mind I could have used sine or cosine because I've got all 3 sides of the triangle at this point. So since this question involves a compass, we need to quote compass directions, or a bearing. I'll do both, just to show you what they look like. To do this, I'm going to draw the south line here, the southwards arrow, and I'll go from there. This shows that I need to determine this angle here. I'm going to call this phi. And since phi is just the complementary angle to theta, I simply do 90 take theta to get phi. And this gives me phi equals 53.1 degrees. Therefore, the direction of this displacement vector is south 53.1 degrees west. It took me a lot of attempts to not make this S look like the 5, so I hope you appreciate that. And what's sad is that it still kind of looks like a 5, but it's an S. Now, because the question doesn't specify how it wants me to quote the direction, I'm going to show you the bearing way to quote the direction as well, and I'm just going to show you in this little space here. Now, the bearing angle is the angle from north clockwise to the vector, and I've just highlighted with a mini curved arrow here that we always go clockwise from north to get the bearing angle. So now it's clear to see that this orange bearing angle is 180 plus the phi. Therefore, an alternative way to quote the displacement is 5 meters at a bearing angle of 233 degrees. Now we're ready to solve for average speed and average velocity, but first I'm going to make more space, but write the answers to A and B for reference. So recalling that average speed is the rate of change of distance, and substituting the values, this gives us 0.700 meters per second. Now to calculate average velocity, we need to find the rate of change of displacement. So therefore, and substituting the values and solving gives us 0.5 meters per second, but we need a direction now because velocity is a vector, and this is just going to be the same direction as the displacement. So south 53.1 degrees west, or as a bearing 233 degrees. And that's it. Here we're going to look at a common unit conversion for speed or velocity, and this is from kilometers per hour into meters per second. It will be more clear if we write the kilometers per hour here in fraction form, as so, because kilometers per hour simply means kilometers divided by hours. So let's convert the kilometers into meters and hours into seconds, because we want kilometers per hour into meters per second ultimately. 1 kilometer is 1,000 meters, and 1 hour is 60 squared seconds, or 3,600. And if we do some simplification here for the 1,000 and 3,600, now to rearrange for meters per second, or m over s, we simply multiply the 3.6 across. So I've written it like this, so that it's clear to see that 1 meter per second equals 3.6 kilometers per hour. And writing these units conventionally to the right here, so we can see that to convert from meters per second into kilometers per hour, we multiply by 3.6, but to go from kilometers per hour to meters per second, which is probably a more common conversion because we generally want to convert to SI units, meters and seconds, we would divide by 3.6. I've just drawn a little conversion diagram here to make it more clear. And as a physics student, it's worthwhile memorizing this conversion as it's quite common and not generally provided. Let's finish this video by looking at the difference between average speed and instantaneous speed. Now we finally get to explain why we've been calculating average values thus far. And it's because the formula we've been using to calculate average speed and average velocity only consider the initial and final positions of the motion. They don't provide information about the motion at particular points in time during the journey. So this warrants the introduction of a new quantity to accurately analyze motion, and this is instantaneous speed, or velocity for that matter. And this is the speed of an object at a point in time. For example, speedometers measure instantaneous speed, the ones in your car. Because when you look at them while you're driving, they are telling you your speed at that current point in time. In 2009, Usain Bolt set the world record for the fastest 100-meter men's sprint, and his time was 9.58 seconds to three significant figures. This is only slightly quicker than my running time. And it's quite sensible to set the origin at his starting position, initial position xi is 0, and also we'll start the time at 0 when he started running. Since we have values for ti, tf, xi, xf, we can calculate the average speed for Usain Bolt's run. So his average speed for this sprint was 10.4 meters per second. So the way we interpret this result for average speed is that on average, Usain Bolt ran 10.4 meters every second. Now this would only be true in reality if he was running at a uniform or constant speed, but he wasn't, because he must have started at 0 like everybody else. Then he would have had to run faster and faster and faster to some maximum speed and then try to maintain that speed until the finish line. So his speed certainly wasn't constant, so this is only an average and shouldn't be taken literally for his motion. So it's incorrect to say that Usain ran 10.4 meters every single second. Or if I convert this speed to kilometers per hour by multiplying by 3.6, we get 37.6 kilometers per hour. So does this mean he actually would have run 37.6 kilometers if he ran for 1 hour? Of course not. This is just an average value. He would almost be fined if he ran at this speed in a school zone during school hours. So I guess an interesting value would be, what was Usain Bolt's maximum instantaneous speed during this sprint? And analysis shows this was 12.3 meters per second, and this occurred at around the 52.5 meter mark. So this speed is actually his speed at this particular point in time, and this is measured using computer analysis. And you can see I've just denoted instantaneous speed with V subscript INS for instantaneous, and in brackets maximum, just to show that it's the maximum instantaneous speed. And I'm sure he would have tried his best to maintain this speed until the finish line. And if we convert this into kilometers per hour, it turns out he would have actually been fined if he ran at this speed in a school zone during school hours. So we've learnt that Usain Bolt is very fast, and that there is a difference between average speed and instantaneous speed. Average speed is your speed on average over a distance, whereas instantaneous speed is your speed at a specific location at a specific time. Thank you for watching this video. If you found it helpful, please like and share it, and subscribe to my channel for more. Also, click the link in the description below to buy your copy of Physics Foundations. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Thank you.